right, so we're here for part 2 of the video on how to draw Lewis structures. I don't know if you're going to try the British accent again.
Hey, man.
Okay, I'm just going to leave that alone. That's if it's racially insensitive, we apologize. Anyway, what are these?
You got these weird shapes, and I think we were talking about effective pairs in the last time, and it looks like we've got 2, 3, 4, 5, 6 effective pairs. So this is as far apart as they can be?
Yeah, so one of the things that we talked about is that electrons on atoms want to be as far away from each other, right?
They don't like each other.
They don't like each other at all. And so our goal is to keep them as far away from each other as possible. Now, the A here, and we're clever with our naming system here.
Atom.
The A stands for the atom in the middle. And these lines represent either bonds or non-bonding electrons.
Electron pairs.
So electron pairs. So what you need to be aware of here is that over here, it could either be an atom or it could be a pair of electrons. These lines themselves are not etched in stone. So the best way to keep two things as far away from each other
180
is a straight line. And I should probably write the angle of this on here because
that would be like 180 degrees.
180 degrees. You cannot get any farther apart.
On this one, when they're in a plane, you got 3, you have 120 degrees. That's as far apart as
and you can probably acknowledge that if you have them set up like this, you are going to be, this is the farthest apart you can keep anything ever.
And this one we did just in the last one, so that's the 109.5 degrees.
And remember, this is the terrible way of doing it would be this.
Because that's only 90.
That is only 90
degrees.
degrees.
109.5.
But one of the things we have to watch today, I'm going to take the very high-tech towel of wiping here, is that this right here is called linear. This right here is called trigonal planar, because why say triangle when you can say trigonal?
Triangle planar, trigonal planar.
Trigonal planar. This is called a tetrahedral or a tetrahedron, depending on...
Now we have 5. And by the way, the dashed lines means behind the plane, and then the coming out is the coming away from you, or the thick triangular line.
It's coming out right out.
And this is a weird one that has 2 different kinds of angles, doesn't it?
Yep.
It's got 90 degrees, so it's like a triangle in the plane. So this is called trigonal. I love that word. Trigonal bipyramidal.
You will understand what that looks like when we actually start drawing the structures out. And then finally over here we have an octahedral. The angles, by the way, he was about to do these here. Oh, yeah. There's a 90-degree angle between the middle and the top, and around the center you have 120. And on this one, it's the best of everything. Every single angle is 90 degrees.
This is the one that looks like this. It's like in your XYZ plane from math class. X, Y, and then Z, and everything's 90 degrees.
That's perfect.
Now we're going to flick and we're going to talk about, fill out a chart. So you each have a chart. So open up to the packet in the chart, and you're going to fill this chart as we go through it. All right, folks, we're at the chart. So that's this chart right here that you're going to want to grab out of your packet, and this is what you're going to be filling out as we go forward. So first of all, 1, 2, no, I did it last time. 2, 3, 4, 5, and 6. All right, so what happens if you have 2? Now, what does this 2 mean?
Well, really quickly, we said that effective pairs are either atoms or electron pairs that are around the center.
So this is the effective pairs.
This is the effective pair. So I'm going to show, if you can see this right here, this is an example where we have a central atom and we have 2 other atoms on the outside. So by definition, these 2 atoms are effective pairs, so we have 2 things around the center.
So this is called linear, write this down, triatomic. So you have 2 effective pairs, and they're bonded.
All these here are they're involved in bonding.
And a classic example of this would be CO2. So I know the Lewis structure. I'm drawing the Lewis structure. You can put that in.
And I've recreated that here.
And there's carbon dioxide. So this is what it looks like. Notice it's got the double bonds, but it's got 2 on 2. All right. But now we can go to a 1 unbonded, right? So in this case, we're going to have it look like this. Got a bond on this side and a pair of electrons on this side.
So literally what we do with this is if we were to take this off, can you grab me one of the white individual white sticks there? All right, so we did this, we're gonna do this in the lab, but we're gonna pretend that this is an electron pair, but do not for a second think that this line
not a bond.
means
That's
a
not an atom.
bond. It's not an atom.
That's an electron pair.
This is an electron pair, we just wanna have it sticking here. So if you take a look at this, we have 1 atom on this side, that's 1 effective pair, but on this side we have an electron pair. So when we describe what we see, we ignore what we see over here. So all we're going to describe is this. Now, fortunately for 2 effective pairs, this is still a line. So we still call it.
Well, actually, I don't know. I always call this linear triatomic and linear diatomic. Well, 2 atoms versus 3 atoms.
Di meaning
2.
And tri meaning?
Yeah, so I always call this linear triatomic and this is linear diatomic. They both have 180 degrees. But let's graduate to 3 effective pairs. Now we did that in the previous business. But in the 3 one, we're going to have, it's going to look like that. I'm going to attempt to draw this. You should do this. It's going to look like this, right? And each of these angles is 120 degrees. We looked at that earlier. And this is called?
Trigonal planar.
Planar.
Trigonal, by the way, is just a fancy way of saying triangle.
Do you see how that's a triangle in the same plane?
Correct.
Okay. Now we're going to flick this around and we're going to take off one of the bonds and add an electron. Oh, by the way, a classic example of this would be what? Trigonal planar.
Something like
SO3 has this particular, I think, right? No, it's SO3 negative 2.
SO3 negative 2, and also an example would be BH3 or something like that.
BH3. These are some examples of molecules that would have that. But now we're going to take off one of those.
So if we take off one of these, and incidentally, we're going to put this electron pair on here, but when you describe what the shape is, you actually describe the shape as if the electron pair wasn't there at all.
So this looks like Mickey Mouse. Mickey
the
Mouse head.
Right.
And the Mickey Mouse head, we say it's bent. I know it's weird. Next, I would call this bent 120 degrees because the angle here is 120 degrees. That's actually not completely true. It turns out that a unbonded pair takes up a little bit more space because he lives a little closer to the central atom, so he pushes, so it's probably like 119 or something like that.
So if you take a look at this right here, the way they are, if you had something here that was pushing a little bit farther, and let's say wouldn't snap these would actually get tucked in a little bit tighter.
All right, and then we move to the next one. We're going to take off one more again. And it's going to look like this, but we're going to have 2 extra pairs of electrons. So it's still 1, 2, 3 effective pairs of electrons on the outside. And this is going to be back to linear diatomic.
And if you take a look at it, right now this just looks like a one-legged nothing. But if we were to put this back in here and replace this with electron pairs, because this is actually what's happening, on these sides we have these electron pairs that are occupying this space. I can't do this very well. So this is kind of what it looks like.
But we only look at it when it's looked like this. So it's just orange and gray.
We are ugly towards electron pairs. They mean nothing to us, although they hugely impact
They
our shape.
impact it, but they don't make a difference.
Now, once you get down to this, is there any way you can take any more things off of this?
No,
pretty much,
at that point you're done. So
Yeah.
once you get to linear diatomic, you might see a pattern here, linear diatomic, you're basically done. Well, let's flick now to 4. 4 gets a little more complex.
All right, 4. I think we're going to do it like this.
So this is the tetrahedral shape that we looked at before, and you can see me drawing it right here. Of course, this is a much better diagram of it, or 3-dimensional rotation. Notice it looks the same way every way he goes, and that's the tetrahedral shape.
And if you notice here, the angle between these is much bigger than if we'd have just drawn the cross like we did on the board earlier. So it's a 109.5 degree angle.
So 109.5, and it's CH4. So now let's flick to that. We're going to take off one of them. So there's 4 effective pairs. Now we're going to have 4 effective pairs, but we're going to take off one and make it a bonding pair. And that's going to look like this.
When he says bonding pair, what he means is this is an electron pair that's not involved in bonding. This right here.
So you can see it looks like this. Now if you look for a moment, if you take this off, this looks like, and it's hard to see for sure, but that's a pyramid. And we don't call it pyramid, we call it pyramidal.
Pyramidal. And if you want to get really fancy, if you take a look at this, see how there's a triangle on the base of this? They sometimes call it trigonal pyramidal. Although pyramidal, usually you can get away with it.
Or you can call it trigonal pyramidal.
Trigonal pyramidal, that's probably, that's the best way to do it.
Now let me say one other thing that's weird, guys. The bond angle is 107 degrees. Because the lone pair takes up more space. So you'd expect 109, so it gets a little bit smaller because the lone pair takes up a little bit more space.
It's repelling more greatly. So each of these 3 guys right here.
And the reason it repels more greatly is because you see this bond, there's an electron here and an electron here, if you will. That electron is attracted to the hydrogen, but these are closer, so they're closer to the central atom, so they're pushing harder, for lack of a better
True
term.
story. So this is what we do when we have.
Well, I think we're going to keep going, right?
Yeah,
so
let's keep on going. So let's rip another one of the legs off of this. And now we have 2 atoms and 2 electron pairs. And again, I would suggest picturing in your mind as if it's still tetrahedral shape, but when we look at it, these electrons here, do they actually exist in terms of the way we look at it?
They exist, but not in terms of the shape. And
So
this again becomes Mickey Mouse again. But now this Mickey Mouse is a little different. In this one, it's bent, notice I wrote 104.5, because again, the angle keeps getting smaller, where if you recall, this was bent 120, which actually is like probably 118.
Mm-hmm.
But it's 104.5 in the classic molecule of water. Water looks like Mickey Mouse head. Okay.
True story. And then if we do the last thing, it's kind of like ripping the limbs off of something, which I get is horrible. Don't rip limbs off of things. But if we pull this last one off, and all we had around this were electron pairs, I'm not going to bother to stick in the 3 different electron pairs, but
Again, guess what you get? Linear diatomic.
we get a linear diatomic, which is, by the way, didn't we have that up there?
well, see, there's a pattern: linear, die, linear, die, linear, die.
So when you get down to just one atom attached and everything else are electron pairs, you're going to end up with a straight line.
Well, let's do the last two, 5 and 6, at least these two right here. So we've got ones where we do 5 connections. Now this is a little bit more tricky, so you're going to have a hard time drawing this. What you want to do is you want to draw. I'm trying to attempt to show you how to draw this.
Whilst I rapidly try and create that particular structure we don't have made yet.
I'm trying to draw this. This is a triangle in the plane, and then up and down we get another one. And the shape of this is trigonal bipyramidal. And then the angles are both 90 degrees and 120 degrees.
And this is what it looks like in real world. It kind of looks like a little bit of a seesaw here.
Well, the way I like to think of it this way, do you see that, if you can see, that this is a triangle in the plane, and then coming out of this triangle in the plane, you can see the triangle plane here better, is you've got the 2 atoms on either side. So,
by the way, we just a happy chance that these were different color. It does not mean anything.
they could all be yellows.
They could all be yellows. They could all be the same atom.
And then we're going to jump to the last one. This is we call it the octahedral, if you call it. And this is it's the 90-degree one. So we've got 1, and then you've actually got 4 in the plane. All right, Mr. Bergman will make a great attempt to do this. This goes behind, this is coming out at you, and then this comes up and down. And this is an octahedral. And they're all 90 degrees.
So this right here, if you take a look at it, there's 90, no matter how you rotate it around, every single angle is 90 degrees. Now, these last 2 here, you might notice that we've not gone to all the variations on this. My pre-AP kids, we are going to do these variations, but we're going to end this video right here in terms of we need you to be able to understand if there's ever 5 effective pairs around a central atom.
Trigonal bipyramidal.
And if there's ever 6, you can
octahedral.
And that's it.
Octahedral.
And that's it.
Trigonal bipyramidal.
Do not worry about
6. No, that's weird. 6 is octahedral. I thought octahedral meant 8.
Yeah, and you know what? This is one of the problems I had before. If you take a look at this, it's really weird. It's actually 8-sided. So if you actually were to put walls on the outside of this, there would actually be 4 walls on the top and 4 walls on the bottom. So there's actually 8 sides. If you look at this is the skeleton for it.
If you ever play Dungeons and Dragons, guys, the 8-sided figure is an octahedron, but it's this shape right here. The
that was special shout out to all nerds there. We look forward to hearing.
I'm a geek, I confess.
We pretty much are. Anything else we need to add to this video?
We're good.
All right. Good luck with this stuff. Make sure you fill out your notes with this, and there'll be a couple of problems that I want you to answer.
People, you must do this.
I do not know what that was, but at the very end, there's going to be a couple of problems. Make sure you draw them on a separate sheet of paper. Have a great night.